Prime numbers. They're like the basic atoms of arithmetic, the building blocks for every other number. But here's the thing. When you actually look for them, they seem scattered completely at random. So in this explainer, we're going to peel back that layer of chaos and ask, what if it's not random at all? What if there's a hidden architecture underneath it all? The answer? Well, it might just change the way you see the universe.
All right, so let's just dive right into the big one, the question that's been bugging mathematicians for millennia. Are the primes really just thrown randomly across the number line, or is there some kind of secret pattern, a hidden set of rules that decides exactly where they pop up?
And right there, that's the paradox that makes them so fascinating. On the one hand, a prime number is a super simple concept. We know exactly what makes a number prime. That's the deterministic part. But on the other hand, the sequence they make, 2, 3, 5, 7, 11, 13, it feels completely unpredictable. The simplest rules seem to create the most complex puzzle. Okay, so let's really dig into this paradox. How can something so fundamental, these basic building blocks, create a sequence that just looks like a total mess?
Well, here's our first big clue that something else is going on. It's called the prime number theorem. And what it proves is that even though you can't predict where the next prime will be, you can predict their overall behavior on a massive scale. They get rarer and rarer in a very specific, predictable way. So it's like our first glimpse of a grand cosmic order hiding behind all that local chaos.
So, this idea of a global order, it's really exciting. It makes you wonder, right? Could there be a map to the primes? And well, that leads us straight to arguably the most famous unsolved problem in all of mathematics.
So way back in 1859, a mathematician named Bernhard Riemann comes along with this just wild idea. He was studying this thing called the zeta function, and he found these special points. He called them the non-trivial zeros. And here's the crazy part. He suggested that the exact locations of these zeros are like a secret code that tells you where every single prime number is. You can think of them like musical frequencies. Riemann's hypothesis is basically that these frequencies combine to create the perfect song of the primes.
And if you thought that was weird, it gets even stranger. A bit later, a couple of other mathematicians, Hilbert and Polya, took it a step further. They were like, okay, if these zeros are like frequencies, maybe they're real, like from the physical world? They actually guessed that these abstract mathematical points behave exactly like the energy levels inside a quantum system. Now, at the time, this was pure speculation, a total shot in the dark.
And for decades, that's all it was. A really cool but totally unproven guess. Until 1972. A chance conversation at the Institute for Advanced Study changed everything. And believe me, this is where the story gets really interesting. Okay, so picture this. There's this young mathematician, Hugh Montgomery, at a meeting. He's explaining a new formula he's just figured out about the statistical spacing between those prime number frequencies, the Riemann zeros. And sitting in the audience is this legendary physicist, Freeman Dyson. And as Montgomery is talking, Dyson has this sudden jolt of recognition.
And you just can't overstate how stunning this next part is. The formula that Montgomery had cooked up, deep in the abstract world of pure number theory, it was identical to a formula that physicists use to predict the spacing of energy levels inside the nucleus of a heavy atom like uranium. The math wasn't similar, it was exactly the same.
Dyson himself was absolutely floored. He later said he could only describe the connection as just a miracle. And you can see why. How could the rules governing abstract numbers possibly be the same as the rules governing the quantum guts of an atom? It was this mind-blowing link between two worlds that should have had nothing to do with each other.
Okay, so the big takeaway here is that this quantum connection, it isn't some weird one-off fluke. It's actually just one piece of a much larger puzzle. It turns out there's a ton of other evidence that all points to this deep hidden order within the primes. Let's look at some more of it.
So check this out. It's 1963, and a mathematician named Stanislav Ulam is just, doodling during a boring meeting. He starts writing numbers in a spiral, 1, 2, 3, 4, and so on, and then he circles all the prime numbers. He's expecting to see just a random mess of dots, but instead, he sees this. The primes, just out of nowhere, start lining up on these clear diagonal lines, a totally unexpected geometric pattern hiding in plain sight.
And it doesn't stop there. The primes also obey this really weird statistical rule called Benford's law.
Basically, this law says that in a ton of real-world data sets, like stock prices, population numbers, you name it, the number 1 is way more likely to be the first digit than any other number. And what do you know? If you look at the prime numbers, they follow Benford's law almost perfectly. It's like they're behaving like a natural phenomenon.
And if you thought that was strange, recent discoveries are even wilder. Scientists can now measure the complexity of a pattern, and they call it a fractal dimension. Now, a simple straight line has a dimension of exactly 1. Total randomness on that line would also average out to 1. But the primes? They measure in at about 0.99. That tiny difference means they have this incredibly intricate, self-repeating structure that's, well, it's something in between perfect order and total chaos.
All right, so let's pull all of this together. Where does all this evidence lead us? What does it tell us about what prime numbers really are?
So, back to our original question. Are primes random? And the answer, pretty clearly, is no. But they're not simply predictable either. The best way to describe them is with a term called deterministic chaos. Think about the weather. We know the physical laws that govern it, so it's deterministic, but it's so incredibly complex that we can't predict it perfectly from one day to the next. That's the primes. They follow simple rules, but produce wildly complex, seemingly random results.
So let's just recap the case for structure. We've got the music of the Riemann frequencies, which seems to perfectly match the energy levels in quantum physics. We've got the shocking geometric patterns of the Ulam spiral. We see this deep fractal complexity, and they even follow universal statistical laws like Benford's. When you line it all up, the evidence is just overwhelming. These numbers are anything but random.
And all of this leads to a really deep, kind of philosophical question. When we're studying these incredible patterns in prime numbers, are we just making up clever math in our own heads? Or, given how deeply they seem to be connected to the physics of the real world, are we actually discovering something fundamental about the very fabric of reality itself?